The main chunk of chapter 12 is actually talking about conservation of energy, though. So let's say we have a connected system. If this was a truck on a ramp, we would know exactly how to deal with this. We would say that, over here we have kinetic energy, and up here we have maybe kinetic but definitely potential energy. For a fluid, that also stays true. Right? So we've got this pipe filled with fluid, and the only difference is, since we don't have discrete chunks of water, instead of talking about the kinetic energy of a chunk of water, we talk about the kinetic energy per volume of the water. So we have the kinetic energy per volume. We have the gravitational potential energy per volume. Water also has one more kind of energy, right? 'Cause there's an energy associated with external pressurization. Right? So remember when we first started talking about pressure last week, we said that you can talk about pressure in terms of force applied over an area, or you can talk about it as an energy per volume. And both of those are valid. The units work out exactly the same either way. So that is what we're doing here. So we have 1/2 mv squared over the volume. I'll use hats on the volume here. Plus mgh per volume. And in both of these cases, this mass on top and volume on bottom, well, that could give us density. And this is what we call Bernoulli's equation. That everywhere in a connected and closed system of water, the total energy per volume, not zero, constant. So Bernoulli's equation is just a statement of conservation of energy. The U is just like it was from chapter 7. U is mgh, gravitational potential.
Why is the word constant written there?
Because if you add up all these kinds of energy in a fluid system, it's going to be the same everywhere in a fluid system.
Okay.
Right? So no matter what 2 points in the system you choose, and there's an infinity of points, right? There's an infinity of points to choose from because the water is continuous everywhere. But if you analyze any 2 points, you'll get exactly the same total value of energy. So far we've applied forces to fluids, we've applied energy to fluids. The next bit, in fact, the last bit in chapter 12, is going to apply elastic strains to fluids. So you may remember from chapter 6 that we would write something down like the force required to compress an object is equal to its Young's modulus times its cross-sectional area times the fractional change in length. Does that seem familiar to anybody? Okay. We have something very similar in fluids. And in fluids, we call it not the elastic constant, but we call it the viscosity. So in here, okay, so let me actually draw the picture associated with this, right? So the picture associated with this is you take a rod, maybe, and you squish it down. And you get this delta L. Do you remember that there was also a shear deformation? So you could take something that was, say, square to begin with. There's also bulk, too. Yep, for sure. So you take something that was square to begin with, and you kind of make it do this. Right? And the force, if you apply a force to the top, the amount of force required is equal to the shear modulus times the cross-sectional area. And here, this bit here is the amount you've caused it to tip over. And this bit here is what the length of the base was originally. So this second picture, this is more similar to what we have going in a fluid, where here we've got, say, and the model that we use here is we say that water is undergoing a laminar flow, which means that we can treat it as if it's made up of a bunch of thin layers, right? If we apply a force up here, we can cause a velocity at the bottom, right? And some fluids do this better than others, right? So you may have encountered the idea of viscosity as a measure of how thick and unlikely to flow a substance is. So honey is very viscous and alcohol is very low viscosity. So you may have encountered the idea that viscosity is a resistance to flow. And that is true. That's a perfectly valid perspective on viscosity. Another way to think of it, though, and this is how physicists usually think of it, is viscosity is how well do forces get translated? Yeah, translated. How force? right? So physicists usually think of it in terms of forces or momentum, right? So we have the impulse momentum theorem from chapter 8, right? A force applied for a time causes a change in momentum. And this is basically what we're thinking about here. If we apply a force to one level in a fluid, is that going to cause a velocity at a different level in the fluid? And in general, the answer is yes. And the relationship there looks very much like one of these elastic strain relationships. So the amount of force you have to apply to get a velocity at the bottom depends on the area over which the force is applied. It depends on the distance between where you're applying the force and where you want the velocity to happen. And then lastly, there is the viscosity. Right? So instead of we have Young's modulus, we have shear modulus, we have viscosity. And this, by the way, is the Greek letter eta. I don't have any idea why we chose eta for viscosity. It is, I just think that eta probably wasn't doing much. So when we were looking around for variables, we're like, eta, you don't look busy. You're viscosity now. Yusuf, exactly. This is another thing you just have to look up, right? We treat it exactly the way we did for the strain problems. You just look up the what the viscosity of a fluid is. Yes, we are being recorded right now. I have to try really hard not to geek out on viscosity because measuring viscosity was actually a large part of my PhD research. All right, so the thing that we really are going to want viscosity for in this class, though, is something called Poiseuille's law. And I always have to look up how to spell this MFer's name. Why can't the French do anything easy way? Okay. Here's the idea for Poiseuille's law. If we have a fluid flowing, and for some reason there is a difference in pressure between these two regions here. Right? If there's for some reason there's a sharp break in pressure, right, so that these two regions are not exactly connected, and this could be for several reasons, right? It could be we have a water pipe that is, connected to some system over here, but then it's open to air on one end. So we're going to be going from whatever pressure is caused by this water column which is in here, to just 1 atmosphere of pressure on the outside. So that's one possible cause for something like this. What you all are usually more concerned about is that there is some sort of membrane between two systems. And this is the law that actually governs how quickly your IV drip will be transferred into your veins. Right? So it's kind of like this blue picture we've drawn here, where the column of water is because you've put the IV above somebody's body, right? So there's some height associated with it. But when it gets to the needle that goes into the person's vein, the pressure on that side is just their blood pressure. So if we need a precise delivery of IV fluids, we can use Poiseuille's law to do this. So here, Q is the flow rate, right? Again, I don't know how Q got conscripted for this duty, because Q also gets used for heat transfer. So it does seem a little bit short-sighted to use it for fluid transfer and heat transfer, but, I didn't make the rules. So the rate at which fluid goes from one part of the system to the next system is equal to the difference in pressure divided by the flow resistance. Okay. And the flow resistance is given in terms of viscosity. So 8 times eta times L, where here L is the length of the interface of the tube that you are trying to force this fluid through across the pressure interface. And on the bottom, pi r to the 4th. Okay. Questions or comments?
What's the 8?
The 8 has to do, like, the 8 comes about when you do the integral to find this value.
Okay.
If you are interested in a more complete answer than that, there is a section on the Wikipedia page for Poiseuille's law that gives the derivation. Okay, so that's all the stuff in chapter 12. We are not going to do turbulence. So basically, I think 12.5, 12.6, 12.7, we won't be doing.
I have another question. I know you said square tubes are ineffective earlier, but what if it is a square pipe?
That's fine.
So what would R be?
So if it is a square pipe, that actually changes the 8 out front. So the 8 comes about because we're assuming it's a circular pipe. But if you have a square pipe instead, you can look up a different expression for flow resistance for square pipes. Jolyn, yeah, we're going to skip 5, 6, and 7 from chapter 12.
Thank you.
But yeah, so the flow resistance given in the book and that I wrote down here is for round pipes. Engineers have definitely come up with expressions for other shapes of pipes, but yeah, you have to look it up. Okay, let's do a couple of problems. And I'll try and pick out the medical ones for you guys since I know that's what you are really interested in. Alright, so we have a major artery and a bunch of little smaller arteries. The very first thing that we talked about was flow rate, um, and we remarked that the flow rate, which is defined by the cross-sectional area times the velocity, that's going to be constant for every point in a connected system fluid, or system of fluid. So in this case, the cross-sectional area of the major artery is 1 square centimeter, and it's got some velocity. That's going to have to be the same of A times V in the smaller arteries. Now, each of the smaller arteries has less cross-sectional area, but there's a lot of them. So the total area, it goes from 1 centimeter squared to 18 times 0.4 centimeters squared. And it will have some other velocity. So the blood will be the blood velocity in the major artery is going to be just over 7 times faster than the blood velocity in the smaller arteries. Questions or comments? Has anyone ever examined their bathroom faucet in detail? You definitely should. So there is water that is pressurized inside your faucet, and then it kind of spills out the edge of the faucet and then falls out. You may have noticed, if you examine it in detail, that the stream of water tapers as it falls toward the bottom of the sink. I mean, yeah, your arteries are basically faucets. Does that bother you? It bothers me that my faucets are basically like an artery. Uh, So if you've examined your faucet, you'll have seen this, that the water tapers and kind of collects together as it falls down toward the sink. And that is because of this reason, that the product of cross-sectional area times velocity is constant. Right? So at the top of this stream, we have some gravitational potential energy. And also some kinetic energy. At the bottom, though, we've exchanged all of that gravitational potential energy for kinetic energy, which means that the water is moving faster just before it hits the sink than it compared to right when it comes out of the faucet. And if it's moving faster, then the cross-sectional area must be smaller. All right. Let's do some Bernoulli's equation stuff. Okay. We know something about windstorms here in Las Vegas, too, don't we? All right. Approximately what is the force on a roof that has an area of 220 square meters? This is, I think, something like a 3,000 square foot house. So it's, it's big, but it's reasonable. Using Bernoulli's okay, so here we go. You also may have noticed, if you follow the weather, that during a windstorm, the air pressure drops. And of course, that is a consequence of Bernoulli's principle. So we have a roof. Here's a house. Inside the house is 1 atmosphere of pressure. Pushing up on the roof. Outside is some other amount of pressure. Right, so what's the net force on this roof? So they tell us what the atmospheric pressure is outside, but we don't actually need them to give us that number. We can find it with Bernoulli's principle. So the pressure in still air, right? And here, so remember, so we have pressure plus speed plus change in height, and those are going to be equal at any 2 points in a closed system. Now, in still air, there is no velocity. And we're not going to be thinking about any change in heights. So instead, we have the pressure of still air is going to be equal to the pressure of windy air plus the kinetic energy associated with the windy air. If we assume that the typical air pressure in Boulder is 1 atmosphere, then we have the pressure of still air is going to be 101,300 pascals. The pressure in windy air is what we would like to know, and the kinetic energy associated with the windy air is going to be 1/2 times 1.14 times 45 squared, right? 45 meters a second is really, really windy. That's about 90 miles an hour. So this number here is about 1100. And so this is the pressure drop that is associated with windy air, right? So if you've got air traveling at this speed, the air pressure drop that you're going to experience is going to be about a kilopascal. Does that make sense? Yes? Maybe? Yeah. Let's actually... I'm going to get rid of the question. There's a lot of extra information in there that we don't actually care about. So the first question is actually, what is the difference in pressure between still air and windy air? Right, let me clean this up. So in still air, we have pressure. We do not have any kinetic energy associated with the air because it is still. The wind is not blowing. Right? This is just Bernoulli's equation. If the air is windy, on the other hand, there is still going to be some pressure, but we also have energy associated with the wind. And Bernoulli's equation says that these two expressions have to be the same. Let's say that we're not, we're comparing still air and windy air at the same height. So actually, these two terms will cancel. And what that means is that the air pressure in the still air is going to be equal to the air pressure of the windy air plus the energy associated with the movement of that windy air. Does that make sense so far? Okay. So what I want to say is, well, what is the difference in pressure due to between the still air and the windy air, right? And that is going to be equal to the kinetic energy that is being, that is the amount of energy going to kinetic energy in the windy air. Right? And if we're using SI units, right? So the units here are kilogram per cubic meter, and the units here are meters per second. Then what we'll get out is the SI unit for pressure. So we're looking at, about a 1 kilopascal difference, like 1,150 Pascal difference in pressure between still air and windy air. And this is approximately what you'll see when we are getting, some really windy weather. If you follow the weather, you'll know that one of the things that gets reported on weather sites is the atmospheric pressure on a given day, and you can go through and you can look at what the atmospheric pressure is. And for very windy days, the atmospheric pressure is going to drop a full percent because of all the energy that goes into, moving the wind. This is, by the way, the principle that sails and wings work on. So I know we are out of time, but I would like to share a YouTube video with you. Just watch it later. And I have plopped it in the chat for everybody. So yeah, take 5 minutes at some point over the weekend and just investigate how sailboats actually work. It's really interesting, and it's not what you would expect. All right, everybody have a good day and a great weekend. I will not see you next week. Next week there is no class due to Nevada Day, but I hope that you all have a great week.
Professor Wolves,
Yes.
just a quick question. If you have time, is there a way that you can add like a toolbox that we did for this session and then from last week's as well, just so my formulas are tracked correctly for the next exam?
Yeah, for sure.
Okay, thank you
Let's do
so
that.
much.
Do you want to do that now, or do you want to do
Oh
that?
yeah, we can do that now. Yeah, just so it's in the I'm assuming this will be still in the recording, so when I rewatch it later, I can just
Yes, it will be.
thank you so much.
Yep. You are very welcome. So the tools that we learned last week are we learned about Pascal's principle. So pressure is the same in every direction. We learned that there is a pressure associated with depth, and we know now that that is a special case of Bernoulli's equation. So you don't actually have to remember that. And we learned that the buoyancy given to an object which is floating is equal to the weight of the water which is displaced. This week, we learned about continuity of flow. We learned about Bernoulli's equation. And we learned about Poiseuille's law, where R for round pipes is equal to 8 times the viscosity times the length of the pipe over pi times the fourth power of the radius of the pipe. That's it. That's everything we've learned in the last two chapters.
Thank
Professor
you. Have
Wolf,
a good weekend.
Yes?
hi,
Hello?
hi, Professor. Did you say last week that we were just going to do homework problems 11 through 7 or 1 through 7 in chapter 11? Did I hear you right? I wrote that down and I don't know why I wrote that down.
Yeah, so in chapter 11, we will. I'm not going to. We excluded 11.8 and 11.9.
Okay. Okay, great. Just wanted to be sure. Thank you.
You're welcome. Uh, Yusuf, you had a question about submission?
Uh, can you hear me?
Yes, I can hear you.
So I was like looking at Canvas and I opened up like the PDF viewer and my answers looked really small for some reason.
That happens. If that happens, I download it and zoom in on it.
Okay, sounds good. But if there's any like issues, just like let me know and
I
I'll
Yeah, I will do that.
thank you.
Yep, you're welcome.
Dr. Wolfs,
Uh huh.
I was gonna ask you. So since we're gonna go over 13 and 14, or we have to, well, since I'm gonna be doing those problems, is it okay if I email you and ask you for the toolbox equation for those? Because that would really help me when while I'm doing the problems. Is that okay?
I can't promise I will get back promptly, but it is okay for you to email me about it.
Okay, and then yeah, okay. Thank you so much.
You're welcome.
Bye.
Bye.
Have a good day.
You too.